Hello, I'm Patricia and I'm here today with my friend Héctor, remotely of course, and we are going to talk about the project we have been developing for the past 4 to 5 months for the DLAS subject, Deep Learning for Acoustic Signal Processing subject. In particular, we are going to talk about the task of automatic language identification. From now on, it will be LID task for short. So I'm going to start with the presentation. In this first slide, we can see the contents of the whole presentation. We are going to go step by step in the process of the whole project. So the first thing to talk about would be the task itself, defining it and explaining why we chose to work with it. The next step would be to show how we divided the process, which steps did we take to get the final results. We couldn't start modeling our network without looking what has been done until now in this task, so we will present a brief description of the state of the art. Then the network itself, so we will talk, for example, about the hyperparameters that we chose to work with. Then the final evaluation of the network, showing the results we came up with, and the final conclusions. So to start with, why did we choose the LID task to talk about? So when searching for acoustic application fields using deep learning techniques, we came up with a lot of tasks that have been improved thanks to these algorithms. For example, audio classification, music recommenders, speech modeling. We also tried some of the class assignments that were uploaded to the Moodle platform. For example, the machine learning on raw audio one, which consisted on extracting the MFCC's features from the raw audio to use as input of a machine learning model to classify vowels. There was another one which used deep learning techniques. It used like 3 dense layers to classify vowels too, but in this case, instead of the MFCCs, we used the MEL filters bank, which is another kind of characteristic from this from audio. In implementing this script, we learned that we don't have to use the whole audio segment we don't have to use it as input of the model. We have to extract some features, some things that characterize that audio to use as input of the model. So it helped a lot trying these class assignments. Then I want to say that we did have a little background in this field, since when I did my bachelor thesis, I implemented a voice activity detector using deep learning techniques. In my case, I used a dataset, which was a fireman's performance. So it was a really dirty dataset. It had a lot of noise, and I used RNNs and DNNs to try to classify if there was voice or not. So I enjoyed it a lot, and I learned a lot about deep learning techniques in the acoustic field. And so to summarize all of this, we found a field which is called Natural Language Processing, NLP for short, which studies how computers analyze and process data referred to language, to human languages. We can find some of its applications in the slide, for example, machine learning or machine translation, sentiment analysis, and the one we chose, which is LID, which is language identification. We chose it because basically we like languages a lot and it sounded quite interesting. So, well, as its name says, it consists on recognizing which language is being spoken in a audio segment. As every deep learning task, every deep learning project, there are some steps that we have carried out that basically match the steps of the contents of this presentation. We have spoken about what we learned from Moodle, from the internet. We will speak in the next slide about the state of the art, then the data analysis, the network modeling, and the final evaluation. We can see in this picture a LID system, which basically uses the audio to extract features, different features, to train the model and to finally classify the language, identify the language. Looking to the state of the art of LIT systems, talking about machine learning techniques, we found out that GMMs, in combination with UVMs, GMMs are Gaussian mixture models and UVMs are universal reference models. Both in combination were widely used to solve this problem, but they had a problem in high dimensionality and in needing lots of data from different sources to have better results. So this was solved by extracting I vectors, which basically represented really well the language information in low dimensional space. When talking about deep learning, that it is what we want to model, we have seen that every type of main neural network has been used: CNNs, DNNs, RNNs, CNNs in combination with RNNs, DNNs using I vectors too. For example, CNNs are widely used to transform the input data into an image which represents, for example, MFCC's features. We have seen that there are lots of features that we have, as we have already said, but the most widely ones used are MFCCs. And as we don't have the resources or the time to try every single type of neural network combination, we have decided to use the most widely ones used, which are LSTMs, long short-term memory network, which is a kind of recurrent neural network which has memory, as its name says. We think that RNNs are widely used because of the type of input data. Audio data isn't static, and sequential type of data is better analyzed by RNN models. So this is why we are going to use those kind of neural networks to model our system. Based on experience, we went to Kaggle to look for a database which consisted of audio files. We found one in a competition called Spoken Language Identification, which had speech samples of English, German, and Spanish languages separated into training and testing sets. We divided the training one into training and validation sets, using a 20% of data for validation. So this next slide is just a brief description of each of the samples that from the database. We can see that the file name specified the language, the ID, the transformation the audio suffered before being uploaded to the Kaggle competition, the sample rate which will be used when we extract the MFCC's features, and all of this kind of information about the codification, the bit depth. Finally, I'm going to talk about the preprocess that the dataset went through before creating the input to the model network. This is basically the most time-consuming step and one of the most important, since the results will depend on this directly. as we have already said, we have extracted the MFCC's features from the audio. We can see in the slide this image about the process of extraction of MFCC's features, but there are tools, there are libraries in Python which provide functions to extract MFCCs, to extract spectrograms, filter banks. So we use this famous library, which is Librosa. And then the dataset suffered from a normalization, since we had disparate values of MFCCs. And finally, the labels were encoded. I think English was 0, German was 1, and Spanish was 2.
Hello, as my teammate said previously, I'm Héctor and I'm exposing the second part of the presentation. As it is explained in the report, we have worked with long short-term memory networks which have into account the context for predicting. That is, the output of the model does not only depends on the current input but also of the past outputs obtained in that session. In this slide, we can see an example image of a long short-term memory neural network. In the system, we can less or more see how the outputs of the hidden layer are stored in memory registries in order to use them as inputs for the calculation of the future outputs. We can see also a summary of one of the models that we have implemented. Here we can appreciate 2 LSTM layers and the dropout that has been applied to them. We can also see a final dense layer. This layer is in charge of making the final classification of the models. In this table, we can see how the configurations of the different experiments that we have carried out. From left to right, we can read the number of LSTM layers, the number of epochs of the training phase, the batch size, the optimizer of the model, and the dropout applied to the LSTM layers. We have decided to change some hyperparameters of the model to check how these configurations affect the results. We have used multiple metrics to analyze the result obtained on each experiment, but we want to highlight the accuracy and loss values obtained during the training and testing, as we consider that these metrics give us a better perception of the effectiveness of the models. The model with which we have obtained better results is the first one, obtaining an accuracy value of 67% when it has been proven against the test set. And the model that have performed the worst is the third one, in which we have obtained an accuracy value of 52%. In this slide, we can see the loss and accuracy graphs of the training process for the best and the worst models. We can see how both the training accuracy and the validation accuracy converge, existing a slight difference between them in the point of convergence. And we can also see how the validation graphs oscillate with a higher amplitude in the validation graphs oscillates with a higher amplitude than the training graph. In this slide, we can see the evaluation metrics in the left and the confusion metrics in the right for the best and the worst models. We can see in both of them how we obtain better results in our implementations in predicting the class 2 language, which corresponds to English. We don't know why this happens, but it is interesting to mention it. And in this slide we can see, or we can read some conclusions that we have arrived. We have good accuracy results less or more, despite the lack of computational resources of this situation. The results are likely to improve if we could train more time and more epochs, and that could be done with more resources. Neural networks, we have learned that tend to overfit. As we can see in the results, we obtain much better results to the in the training and validation phases than in the test phase. In this problem, we can also learn, or we have learned, that LSTM layers and dense layers work together, as in this case that a dense neural network is used in the output of a LSTM layer to make the classification, and we don't know why our models work better in predicting English. Our intuition tell us that Spanish, by its features, should be easier to predict than German and English, or to differentiate. But we don't know why. We suppose that this fact is related to the features of the MFCC coefficients, but we don't know. And thank you for your attention, and that's all.